Modern machine translation systems, like Google Translate, derive their accuracy from volume. They are trained on massive parallel corpora, millions of side-by-side sentences comparing a known language to a target language. Historical decipherment presents the exact opposite environment. When dealing with a dead, undeciphered language, the parallel data evaporates to exactly 0, and total token counts are minuscule. Without a supervised signal to guide the training, standard sequence-to-sequence models simply collapse. The math forces them into linguistically degenerate outputs that look nothing like human speech. Take the ancient Semitic language of Ugaritic. We have limited texts etched in cuneiform, no direct modern descendant, and no Rosetta Stone. Deciphering a lost language without a parallel text means moving beyond standard training methods. It requires a system that mathematically enforces the specific patterns of language change documented by historians. Problem by looking past raw data. Instead of searching for more texts, they took the qualitative rules of historical linguistics and hard-coded them directly into the artificial intelligence. They designed a hybrid architecture split into two distinct halves: a local, character-level neural sequence-to-sequence model, paired with a global, vocabulary-level graph network. Working in tandem, these two systems translate human domain expertise into harsh quantitative loss functions. In zero-data environments, neural networks fail when left to guess in the dark. They succeed only when they are strictly confined by the immutable logic of the physical world. The model operates on 4 specific linguistic priors. The first is distributional similarity. Characters originating from the same proto-language will show up in similar places within words, sharing their contextual profiles across time. The engineering challenge is comparing these profiles across completely alien alphabets. A computer cannot innately evaluate a phonetic transcription of Hebrew against an ancient wedge-shaped symbol it has never seen before. This 3D scatterplot models a universal vector space. Using a matrix equation, both the lost language and the known language drift into this shared geometric environment, projecting as linear combinations to visualize their overlap. By mapping these contextual profiles into a shared coordinate system, the neural network builds a mathematical bridge to compare previously incomparable symbols. The second prior is monotonic mapping. Language evolution is chronological. A P might shift into a B over centuries, but characters rarely scramble their sequential order within a specific word. Standard sequence-to-sequence attention mechanisms lack this physical restraint. To lower their error rate, they will happily jump back and forth across a word to force a mathematical match. To test this alignment problem, the researchers applied the model to Mycenaean Linear B, targeting ancient Greek as the known descendant. This alignment grid maps Linear B against Greek. By introducing a quadratic loss penalty, the system monitors connections. If the attention mechanism jumps out of sequence, this penalty severely punishes the model for multi-character insertions or deletions. The regularization forces the neural network to obey the chronological flow of time, rejecting mathematically cheap shortcuts in favor of linguistic reality. The final priors shift the focus to the entire vocabulary. First, true cognates map one-to-one. Second, ancient vocabulary has surviving matches. Without a global view, a neural model operates too greedily. It might easily assign 5 different ancient words to the exact same known target word, resulting in a structural collapse. This bipartite graph solves greedy mapping via a minimum cost flow algorithm. Edge capacities of 1 enforce one-to-one mapping. Total flow demand D ensures wide vocabulary coverage. Edit distance costs act as a structural safety net, routing hallucinated translations to the closest true word. The flow graph acts as a structural safety net. It actively overrides the neural network's local errors to calculate a globally accurate vocabulary map. This creates a new integration problem for the researchers. You have a neural network guessing characters and a flow graph mapping vocabularies. With zero ground truth data, how do they actually train? Algorithm 1 uses an expectation maximization loop to alternate training. In step 1, the graph is locked while the neural network updates its weights. In step 2, the network is locked, recalculating edit distances so the flow graph finds a lower cost path. To prevent the two systems from locking into an early, degenerate feedback loop, the researchers applied a flow decay to smooth out sparse graph updates, and they periodically wiped the optimizer's memory clean. Through this delicate, iterative dance, unsupervised learning manages to bootstrap its own accuracy from zero initial ground truth. When applied to Ugaritic cuneiform, searching against a known Hebrew lexicon, the hybrid system delivered concrete results. This chart compares the outcome, a 65.9% accuracy rate in identifying cognates. This beat the previous state-of-the-art Bayesian model by a full 5.5%, all without relying on human-provided morphological segmentation. The ultimate stress test was Linear B. Because it is a syllabic writing system, symbols map to phonemes completely differently, breaking the standard one-to-one character assumptions used in alphabets. Despite this structural hurdle, the model achieved 67.3% accuracy on location and proper names in the ancient Greek corpus. By reaching state-of-the-art accuracy across these distinct linguistic structures, the researchers demonstrated that these mathematical constraints can effectively model patterns of language evolution across unrelated families. In the current era of machine learning, the default approach to poor performance is simply throwing more compute power at larger datasets. But when raw data is entirely absent, human domain expertise, whether in historical linguistics, particle physics, or organic chemistry, must act as the substitute. The MIT CSAIL decipherment model serves as a blueprint for AI generation that doesn't just guess patterns, but strictly obeys physical laws. The MIT CSAIL model demonstrates that tying the probabilistic power of deep learning to specific logical constraints provides a path for solving complex problems where raw data is simply unavailable.